So in this video, we're going to talk about the manufacturing processes. The first thing we want to introduce is called the Litto's Law. The Litto's Law is a very useful formulation for the manufacturing process as well as for the service industry process. Basically, the Litto's Law said that the number of jobs or people in the system will be equal to the arrival rate. So it can be the raw materials arrival rate or the people going to the bank multiplied by the average time spent in the system. For example, if we said that on average 5 people arrive to the mountain space in Disney every minute, and there are 450 people in line, then what would be the average waiting time? We can apply the Litto's Law because we know the number of people in the system will be equal to the arrival rate multiplied by the average time spent in the system. So we can calculate the average time spent in the system, which will be the average waiting time equal to 450 divided by 2. And that will be 90 minutes. And there are also other terms that you should know when we are talking about the production process. The first one is the throughput. The throughput tells us what will be the average rate that the item will be flowed through a process and what will be the output rate, essentially. For a stable system, the throughput will be the same as the input rate. And for a non-stable system, the throughput will be the same as the process time of the slowest machines. And we will talk about what a stable system mean and what a non-stable system mean later. The second term will be the flow time. Flow time means the time it takes for each unit to flow through the process, and it includes the waiting time and the idle time between two different stations. The raw material process time will be the time it takes for each unit to be processed, and here we do not consider the waiting time and the idle time. In other words, the flow time will be equal to the raw material processing time plus the waiting time and the idle time in between two stations. And we can also use the Litto's Law to find out what will be the working process or the inventory. And basically, we will say that the working process will be equal to the throughput multiplied by the flow time. So this is a stable system. And if you want to see whether the system is stable or not, the first thing you want to do is to compare the input rate. So 3 units per minute is our input. And for the first stations, the process rate will be 5 units per minute. And the second station will be 8 units per minute. The third station will be 6. And the very last station will be 4 units per minute. If we want to make sure that the system is stable, you first want to make sure that for every single service rate, 5, 8, 6, 4, they are all greater than your input. So our input is 3. We know 5 is greater than 3. All these 4 numbers are greater than 3. So we have a stable system. And once you know you have a stable system, we know the throughput rate will be your input rate. The reason is that when your raw material go into the first stations, because your input rate will be 3, although your first station can process 5 units at a time, the material goes to the second station at a rate of 3 per minute as well. Similarly, it will go to the second station 3 per minute, and it will go to the next station 3 per minute. So the output will be 3 per minute, and that will be our throughput. The raw material processing time will be the time it takes for you to process a material. This does not include the waiting time, so it will be 5 plus 8 plus 6 plus 4. We cannot calculate the flow time at this moment because it depends on the actual distribution of your arrival and the service time of each stations. But sometimes you will have some material sitting between stations waiting to be processed. And when you consider those, and you will realize that the flow time will be much longer than the raw material process time. Once you know the flow time, you can calculate the working process. and using little slow, and we know that will be equal to throughput multiplied by the flow time. And for a non-stable system, you will realize that at least one of the stations has the service rate less than your input. So we know initially the item will go to the system 4 units per minute. And because 5 is greater than 4, so the input for the second station will still be 4. But our service rate will be 8 per minute. We have enough capacity to deal with that. So it will still be 4. Now I have 4 units per minute, but my station can only process 3 per minute. In other words, the third station becomes my bottleneck for now, and my output will be reduced to 3 units per minute instead of 4. Again, when I have input 3 units per minute, but my server can only process 1 per minute, my output will become 1 unit per minute. The raw material process time will still be the same, 5 plus 8 plus 3 plus 1. However, when you have a non-stable system, your flow time will become infinity, and your inventory will become infinity. This is because at the third station right here and the fourth station right here, you will have tons of inventory piling up there because you simply don't have enough capacity to deal with that. Now, let's take a look at the example to see if we can use a little slow to do the calculations. So in this example, suppose we have a assembly line and there are 4 stations. The first station, it can process 10 units at a time. The second station can process 8 units at a time. The third station can process 7 units at a time. And the very last station can process 9 units at a time. And we assume the material go into the system at a rate of 6 per minute. And in the first questions, it says that on average, there are 500 unfinished units in the system. And what is the flow time of the system? We know based on the Litto's law, the working process is equal to the throughput times the flow time. In other words, the flow time will be equal to the working process divided by the throughput. Now, there are 500 unfinished units in the system, which means our working process is equal to 500. How about the throughput? We know the item will go into the system at a rate of 6 per minute. Since the first station can process 10 units per minute, that means the output will still remain as 6 per minute because the input rate is slower than the process rate. Similarly, we can go into the second system at a rate of 6 per minute, but the second station can process 8 per minute, so the rate will still remain as 6 per minute. And we will be identical here. Finally, it will be identical to here, since 6 is slower than 9. In other words, our output rate will be 6 per minute, and the definition of throughput will be your output rate. So in this case, our output will be 6 units per minute. That means our flow time will be equal to 83.33 minutes. Okay? And for the second question, it said that upon leaving station number 1, it takes on average 40 minutes before a unit can be processed by station number 2. So what is the inventory level before station number 2? So basically, in the second question, we still want to calculate the working process, but only for the station number 2. Okay? So we want to know how much inventory will be stay right here. And the formulation will still be the Litto's law. It will be throughput. But again, this is a throughput for the station number 2 times the flow time. And this is the flow time for station number 2. And in this case, we know the throughput will still be 6 per minute. And the flow time will be 40 minutes because in the problem description, it said that it takes on average 40 minutes before a unit can be processed by station number 2, which means the unit will be waiting here for on average of 40 minutes. Okay, so we use 6 multiplied by 40, we got 240. And so on average, our inventory at the station number 2 will be 240 units. And in the third question, it said that what will be the bottleneck stations. Usually, the bottleneck station will be the station that has the slowest rate. So in this case, station number 3 will be our bottleneck. So how much improvement we can make on station number 3? If we increase this rate to 8, and it will still be the bottleneck because it is still the slowest stations. But let's say if we change this rate to 9 per minute, then station number 3 is no longer the bottleneck station. Instead, station number 2 will be the bottleneck station. So if we really want to make an improvement on the station number 3, we don't want to make it at a rate of higher than 8 because otherwise the improvement will be meaningless. So that's a solution for this particular example. Next, let's talk about availability in the manufacturing process. And particularly, we want to discuss the arrival availability and the service availabilities. Usually, when we are trying to compare the availabilities, one thing we can do is to calculate the variance. So we call the VARS as the variance of the processing time and the VRA as the variance of the inter-arrival time. However, there is some issue when you are trying to use the variance because when you have a larger value, the variance will also be higher. When you have a smaller value, the variance will be smaller. So sometimes it can be difficult for you to do objective comparisons in terms of that variance. So one thing we can do is to calculate the coefficient of variations. And so we call CS as the coefficient of variation in processing time. The formulation will be the standard deviation of your processing time divided by your expected value of your processing time. Similarly, CA will be the coefficient of variations in inter-arrival time, and the formulation will be the standard deviation of your inter-arrival time divided by the expected value of your inter-arrival time. Because we consider the value, we consider the expected value of the processing time, the expected value of the inter-arrival time. So when you are trying to compare two different arrival systems to see which one has a higher availability, this can help you get a better understanding to see which one is more variable. So usually when your coefficient of variation is less than 0.75, then we consider the system has a low variabilities. And when the value is greater than 1.33, we consider it has a high variabilities. Anything in between will be the moderate variabilities. And these two graphs can show you what they looks like. Let's say if we have a low variability arrival, basically customer will arrive to the stations with about the same distance. And so they are pretty uniform. And if I say there will be a new arrival every 5 minutes, and roughly it will be equal to 5 minutes. Sometimes it will be longer, and sometimes it will be shorter, but in general it will be pretty close to 5 minutes. But when you have a high availability arrival, then you will look like the picture on the bottom. So sometimes you will get tons of arrival, and sometimes you don't get anything. Then suddenly you will get tons of arrival again. So when you have a pattern like this, it means that you have a high availability arrival. So how does the availability affect your system performance? So let's assume we have two different stations. The graph on top, we assume we have a high utilization stations. when we say we have a high utilization station, it means that the server is always busy and they don't have much idle time. And on the bottom, we have a low utilization stations, which means the server is not always busy. He has some idle time and he can do other stuff without affecting the performance. Okay, so let's focus on the figure on the top. Suppose I have a low arrival availability coming to the system, but when I have a high process availability stations, my low flow availability arrival will become a high flow availability output. Okay, when we see the picture at the bottom, here I still have a high process availability. However, when my input has a low flow availabilities, my output remains as a low flow availabilities. And the only difference between the picture on top and the picture at the bottom will be here. On top, I have a high utilization stations. At the bottom, I have a low utilization stations. So what does that mean? It means that if the process availability is high, if you want to improve the system performance, you need to lower the utilization rate. Okay, so one thing you can do is that, okay, suppose this process is very difficult to handle, so naturally the availability will be very high. So if I want to maintain the system performance, maybe what I can do would be to increase the number of workers or the number of machines to do the job at the same time. This is another example. Let's focus on the one on top. When I have a low availability arrival and low utilization stations and high process availability service, then my output will remain as a low flow availability. But when I have a low process availability, and if my input has a high flow availabilities, my output will remain as high flow availability. So what does that mean? It means that if the utilization rate is low, then you should try to reduce the arrival availabilities. Okay? Because regardless whether you go through a high process availability system or the low process availability system, the output pattern will be almost identical to the input pattern. When the input has low availability, the output will have low availability. If the input has a high availabilities, the output will have high availabilities. So this is a third comparison. Here we have high utilization rate on both scenarios, but on top I have high process availabilities. At the bottom, I have the low process availabilities. When I have a high process availability, even if my input has low flow availabilities, the output will become high flow availabilities. However, if I have low process availabilities, even if my input has a high flow availabilities, my output will reduce to a low flow availability. So the conclusion we can get from this figure is that if the utilization rate is high, so when your server is very busy and you don't have sufficient capacity, you should try to reduce the process availability. So if you cannot hire more people, then you need to make sure you train your workers well, so they will be able to reduce the process availability. Or if you cannot buy more machines, then you better make sure that the machine is well maintained, so you will be able to process the item more consistently. So, whenever you have operations with the highest availability, that should be done as late as possible in the production process. Okay? Because if you put the operation with a high availability at the beginning, your flow will have a high availability throughout the system, and that's not good for your performance. So if something with high availability can be delayed to the end, you should delay that to the very end. Another subject that we want to talk about is the assembly line design. And for the assembly line design, basically, it means that we have a process to create the product, and the process needs you to go through several different activities. For example, we might need to cut the wood, then we need to sand the wood, then we need to pan the wood, something like that. So we want to figure out how many workers or how many workstations we need to have, so we will be able to get the output we want. There are a couple of terms you need to consider. The first one is the workstation cycle time. The workstation cycle time means the time between two successive units coming off the end of the assembly line. So we want to know what will be the time between two products coming out of the system. Okay? And assembly line balancing means that we want to assign different tasks to different workstations, so we will be able to meet the required cycle time and minimize the cycle time. So, couple steps that you want to do. The first thing is to determine the required cycle time. So the question will tell you what will be my work hours and what will be my output requirement. Then you can use the formulation to determine what will be the required cycle time. So I need to know how fast I need to produce the item. Okay. Then we can calculate the theoretical minimum number of workstations. So this number NT can be calculated by sum of the task time. So we first find out what will be the total time required for you to produce one single product. Then we use that to divide the cycle time. This is what we call a theoretical minimum number of workstations. It can tell you theoretically what will be the minimum number of stations that you need in order to achieve the goal. So later on, when you are trying to do the assembly line balancing, your workstation will be higher than or equal to this theoretical number. Then you need to select a couple different decision rules. And for example, my primary rule can be the task that has the longest task time. Or I can say my rule will be I'm going to give the priority to the task that has the largest number of following tasks. Okay. Then you need to assign the tasks one at a time based on the rule you select. Then you need to evaluate the efficiency of your balancing. And the efficiency will be the sum of the task time divided by the actual number of workstations multiplied by the cycle. So this one tells you what will be the total works that will be required divided by what will be the total working force available to me. So basically, you know what will be the percentage workforce that are in effect. So let's take a look at the example. Suppose a company needs to build up 500 toys per day and the production time per day is 420 minutes. We want to balance this assembly line. Now, let's take a look at the first assembly line balancing example. In this example, we know a company needs to build 500 toys every day, and the total production time per day will be 420 minutes. And this figure shows how many different steps that we need to go through in order for you to produce one single toy. For example, you need to finish task A, and the time for task A will be 45 seconds. You also need to go through task B, the time will be 15 seconds. And usually when you face this type of problem, the first thing you need to do is to calculate the cycle time. And how do we do that? The cycle time is C. And in order for you to calculate the cycle time, the first thing you need to figure out how many time you have per day. In this case, we have 420 minutes. And because all the tasks are calculated in seconds, so we want to convert this to seconds. Then we divide it to the total number of toys that you need to produce. In this case, it will be 500. And it will tell you how much time that will be required for you to produce one single toy every day. So that will be 50.4 seconds. Okay? So once you have the cycle time calculated, the next thing you want to do is to figure out theoretically how many workers will be needed for you to finish the text. So how many workers that we need to have in order for us to produce a toy every 50.4 seconds. So to do that, remember on the slide, we have a formulation called NT. That's the theoretical number of stations or the theoretical number of workers that will be needed. And the formulation will be T divided by C. So the T we have here will be the total time required for you to assemble one single toy. So you just sum up all the number on this figure together, 45 plus 15 plus 25, and everything together, we know the total time required will be 219 seconds. And our cycle time is 50.4. We want to round this number up, so we know theoretically the number of stations that we will be needed will be 5. So in other words, you need to hire at least 5 workers in order to reach this goal. Okay? The next thing we want to do is to figure out how to assign those tasks to different workers. We know we probably need to have 5 or 6 different workers, and we need to know who need to do what in order to make sure that everybody has approximately the same load. So to do that, we need to consider different rules. For example, in this case, the primary rule can be the number of tasks that follows. So let's write it down here. Primary rules. In this case, will be the number of tasks followed. Okay? So you just need to figure out how many additional tasks that you need to complete after you finish a certain job. For example, for C, we know after we finish C, we still need to work on D, G, H, I, J, and K, right? So I have 1, 2, 3, 4, 5, 6 after C. So C will have 6 tasks. And we want to do this for every single station, and we sort it from the one has the most tasks to finish to the one that has least tasks to finish. Next, we can check A. After we finish A, we still need to work on B, E, F, G, and K. 1, 2, 3, 4, 5. So for A, I have 5 additional tasks to finish. All right. Similarly for D, let's take a look at D. After I finish D, I need to work on H, G, I, J, and K. 1, 2, 3, 4, 5. So D will be 5 as well. And you do every single one. I will just write it down. For B, we will have 4. And for E, we will have 3. Then for H, we also have 3. For I, we have 2. For F, we have 1. For G, we have 1. For J, we only have 1. K is the last step, so K will have 0. So when we try to assign the different tasks to different workers, we want to go through this list from the highest one to the lowest one. But you probably will notice that at certain points, we will face a tie. For example, E and H, they are both having 3 additional tasks. Similarly, for the F, G, and J, they all have 1 task followed. So when you have a tie, you need to use a secondary rule to figure out which one need to go first. So in this case, our secondary rule, we want to consider the task time, okay? Again, we sort it from the text that takes the longest to the text that takes the shortest time. So in this case, the longest text will be, let's take a look, is C. C will be 50.
The second one is A45. And the third one is E. E will take 25 seconds. Then the next one is G. G will take 20 seconds. And the next one is B, 15. D is also 15. And K is the next one. J, H, I, and B. Okay? So whenever we face a tie in the primary rule, we move to the secondary rule. So we can actually write it down right now. So for example, when we have E and H, which one should go first? We check the secondary rule, E and H. So E comes before H, so we are good there. But when we consider F, G, and J, we know F is, did I miss F? No. I think F is actually I did miss F. F is 5 seconds, so F is the very last one. So this one is not a B. This one is F. Sorry, let me replace that. This is F. That's a small typo. Okay. So when you have F, G, and J, we actually want to work on G first, J second, and F last. So maybe I will cross out F and move to here because we want to work on G, J, then F. Similarly, A and D are both 5 seconds, but A comes before D, so we are good there. So that's the sequence that we want to follow. Okay. Then the next thing you want to do is to add one station at a time until the total time for that worker is approximately equal to 50.4. But you don't want the number higher than 50.4. Okay? For example, let's try to assign the work for the first workers. The first one will be C. So I will assign task C to the first worker. The total time will be 50. And the second one is A. So I'll try to assign A to the first worker as well. But as you can see, if I sum up all the numbers together, 50 plus 45, that will be greater than our cycle time. So that's not allowed. The first worker can only work on task C. So this is the work that needs to be done by the first worker. Okay. Then we move on to the next task because we have already assigned C to the worker. We work on the schedule for the second workers. The first one is A, 45. The next one is D. D will be 15. 45 plus 15 will be 60, which is higher than 50.4. So that's not allowed. That means the second worker can only work on station A job. Then the next one is D and B. We know D is 15 seconds. B is also 15 seconds. So that's good. The sum of these two will be 30, which is far below 50.4. The next one is E, but if we add 30 plus 25, that will be 55, which is higher than 50.4. So that's not allowed, which means the third worker can only work on B and D. All right? So let's move on to the E. We know E will be 25 seconds. H will be additional 10 seconds, so the total is 35. And I is 2. So 25 plus 10 plus 7, I got 40 something. But if I try to add G to that, it will be too high. So which means the next worker can only work on E, H, and I. So this is a job that will be assigned to that. Okay? And so the next one will be G, J, and F. So G is 20, J is 12, 32, F is 5, 37. But if I try to add K to that, it will be higher than 50.4, so I cannot do that. The next worker can only work on these three, which means we have one additional worker who will work on the very last job. What does that mean? It means that I will have 1 worker, 2 workers, 3 over here, 4, 5, and 6. Okay, so theoretically, I should be able to find a assignment such that the job can be assigned to 5 workers. But based on these rules, I need to assign it to 6 different workers. So our n actual number of workers needed will be 6 in this case. Then we can calculate the efficiencies. How do we calculate the efficiency? Efficiency will be the total time that you will need it for you to finish 1 toy. In this case, it will be T, which is 219. And we also want to know theoretically the cycle time is 50.4. If I have 6 workers, that's the total time available to the company. And when we divide that, we figure the answer will be let's take a look of here. It will be 219 divided by 6 times 50.4. Okay, which means the efficiency is about 72.4. And you could probably do better by switching a different rule, which I will show you on the next slide. But if you try to do the assignment based on these 2 rules, that's the best you can get. And you kind of get the idea because for the very last worker, he can only work on 1 task, which will take 15 seconds only. But since each worker should be able to do total time of 50.4 seconds, we know that's not sufficient and there should be a better assignment. And we will discuss that on the next slide.
So as shown in the previous video, we need to have 7 stations in order to balance the assembly line, and the efficiency is 72.4%. But let me show you a different example. Suppose we can change the assignment rule. We actually will be able to balance the assembly line with only 5 stations as shown in these pictures. And the efficiency in this picture will be 86.9%.
Now, let's try a different example. Assume the daily output is 300 units and the assembly line operates 450 minutes per day, and balance the line using the number of tasks as a primary rule and the task time as a secondary rule. So the first thing we want to do is to calculate the cycle time. We know the cycle time is equal to the total time available to you, so that will be 450 minutes. We want to convert this to seconds and divide it by the total output you want to have. That will be 300. So in this case, the cycle time will be equal to 90 seconds. Okay. Then we can calculate theoretically how many workers that you need to have. So that's NT. And we know the total tasks for you to complete the toy or the product will be the sum of those numbers. In this case, that will be 148 divided by 90. We round it up. This is approximately equal to 2, which means if you can assign the different tasks to different workers efficiently, you will need to have a minimum of 2 workers to complete the output that you required. Then the next thing we want to do is to lay out all the sequence based on the primary rule and the secondary rule, then start to assign different tasks to different workers. So let's try to write down the primary rule here. We know the primary rule is based on how many tasks that are followed by each of those. For example, for C, I have 1, 2, 3, 4, 5. Okay, so C will have 5. The next one is actually D because I have 1, 2, 3, 4. And the next one, let's see, it will be H because if you see H here, the following text will be I, J, and K. I have 3. Similarly, for the A, I also have 1, 2, 3. And I also have E. E has 1, 2, 3. And let's do the following. B will have 2. I will also have 2. J will have 1. F have 1. G has 1. K also 1. Oh, sorry, K will be 0. That will be the very last test. So as you can see, we have a couple ties. H, A, E, they all have 3. Similarly, B and I will have 2. J and F and K, they all have 1. So we need to use the secondary rule. The secondary rule will be based on the duration of each text. So we try to sort it from the highest to the lowest. I believe C will be the highest because the duration will be 30, followed by D, A, E, H, B, I, G, J, F, and K. You know, I made a mistake here, so let me erase this part. So the secondary rule will be, we want to sort the secondary rule. We want to sort the secondary rule from the highest to the lowest. So the highest will be C, followed by G, A, B, D, K, E, H, I, J, and F. All right. Then when we combine the primary rule and the secondary rule, then the final sequence should be C, D, A, E, H, B, I, G, J, F, K. So that's the order that we want to follow when we try to assign a test to different workers. So let's start from C. And C duration will be 30. The next one is D, duration will be 15. So the total will be 45. You keep doing this until the total time will be less than or equal to 90. So in this case, we can add C, D, A, H, and E together. So I have C, D, E, H, A. That will be those. This will be assigned to the first worker. Okay. Then the rest will be B, I, G, J, F, K. So we do it one by one. B, 15 plus 7, plus G, plus 6, plus 5, plus 15. And you probably will realize that after all, the sum of those will be less than 90 as well. So I can just select those, and that will be the text to be assigned to the second workers. So in this case, you will realize that we actually only need 2 workers. So our actual number of workers is equal to our theoretical number required, which is also 2. And I can calculate the efficiency. The efficiency will be the total text required time, 148. I have 2 workers. Each one will have a cycle time of 90. So that means my efficiency is equal to 82.2%.